Hey there, folks. Today, we'll delve into the fascinating realm of radar system control and visualization using Python. Let's dive right in. In this video, we'll go through the following topics: Introduction, overview of the code, breaking down Python code, importing libraries, initializing devices and configuration parameters, creating GUI components, handling GUI events and actions, updating FFT and waterfall plot, main execution loop, conclusion, introduction. Let's delve into radar system control and visualization using Python. This Python code is from John Craft's GitHub repository. If you're keen on radar and enjoy electronic projects, you'll love John Craft's YouTube channel. Overview of the code. Imports. The script imports necessary libraries such as ADI, analog devices, Matplotlib, NumPy, Pictograph, and PyQt5 for GUI components. Device initialization. It initializes various devices like SDR, software-defined radio, and phaser, sets their configurations, gains, and GPIO states. Configuration parameters. Sets various parameters such as sample rate, center frequency, signal frequency, number of slices, FFT size, etc. GUI setup. It sets up the PyQt5 GUI with various components like checkboxes, sliders, buttons, and plots for displaying FFT and waterfall spectrum. Callbacks and event handlers. Defines methods to handle GUI events like changing CFAR parameters, setting chirp bandwidth, updating waterfall intensity levels, and ending the program gracefully. Update function. Contains a function to update the FFT plot and waterfall spectrum in real time. Main loop. Runs the PyQt5 application event loop and executes the update function periodically using a queue timer. Importing libraries. The code imports necessary libraries for interacting with hardware components, example, ADI for analog devices hardware, performing CFAR processing, handling GUI, using PyQt5 and Pictograph, and other standard Python libraries. Initializing devices and configuration parameters. Devices such as SDR, software-defined radio, and phaser are instantiated with specified URIs. Initial configurations for SDR, RX/TX, ADAR 1000S, and ADF 4159 PLL are set. Configuration parameters such as sample rate, center frequency, chirp bandwidth, etc. are printed. Creating GUI components. A PyQt5 window is created with various GUI components like checkboxes, sliders, buttons, and plot widgets. The UI components method sets up the layout and adds widgets to it. Handling GUI events and actions. These methods handle various GUI events such as slider value changes, button clicks, and checkbox state changes. They update parameters, toggle settings, and control program behavior based on user interactions. Updating FFT and waterfall plot. Data acquisition and pre-processing. Raw data is acquired from the radar system using my_SDR.RX function. A windowing function, Blackman window, is applied to the raw data to mitigate spectral leakage. The window data is then multiplied with the acquired signal to reduce noise. FFT calculation. The pre-processed data is passed through the FFT algorithm using np.fft.fft to convert it from the time domain to the frequency domain. The magnitude spectrum, S_mag, is calculated by taking the absolute value of the FFT result. The magnitude spectrum is shifted using np.fft.firfshift to center the spectrum around zero frequency. CFAR processing, optional. If CFAR processing is enabled, far_toggle, the CFAR algorithm is applied to the magnitude spectrum to detect targets and reject clutter. The CFAR algorithm thresholds the magnitude spectrum based on local noise levels and identifies potential targets. Detected targets are highlighted in the FFT plot or the waterfall plot. Updating FFT and waterfall plot. Continue. Visualization update. The FFT plot, win.fft_curve, is updated with the latest FFT results. The waterfall spectrum, win.img_a, is updated with the latest magnitude spectrum data. Color mapping adjustments are made to ensure proper visualization of signal intensity. Threshold plot visibility. The visibility of the FFT threshold plot, win.fft_threshold, is toggled based on the value of plot_threshold. If plot_threshold is true, the FFT threshold plot is displayed. Otherwise, it is hidden. Auto range adjustment. After the first update, index == 1, auto range is enabled for the FFT plot, win.fft_plot, to ensure proper scaling of axes. Index increment. The index variable is increment to keep track of the number of updates for auto range adjustment. Main execution loop. QTimer initialization. A QTimer object named timer is created. QTimer is a high-level class for timers that can be used to periodically call functions or update GUI elements. Timer.timeout.connect update establishes a connection between the timeout signal emitted by the timer and the update function. This means that every time the timer times out, the update function will be called. Timer start. Timer.start 0 starts the timer with a timeout value of 0 milliseconds. This effectively tells the timer to emit the timeout signal as soon as possible, creating a continuous loop where the update function is called as frequently as possible. PyQt5 application event loop. app.exec starts the PyQt5 application event loop, which listens for and dispatches events, such as user input, timer events, and window updates, to the appropriate event handlers. sys.exit ensures that the Python interpreter exits when the PyQt5 application is closed. This prevents the program from continuing to run in the background after the GUI is closed. Conclusion. In the video, we explored several topics, such as giving an overview of the code and breaking down Python code. Specifically, we covered importing libraries, initializing devices and configuration parameters, creating GUI components, handling GUI events and actions, updating FFT and waterfall plots, and navigating the main execution loop. Excited to have you join us in the next video? Thank you.